Okay, yeah, so equilibrium is what you guys learned this past Friday. Um, wasn't too complex of a class. He kind of kept it brief, but that is a really important topic to have down now. So um, normally after an exam, the number of people who come to these past sessions does dwindle for a little bit, and then when it gets closer to the quiz, it picks back up. But good on you guys for being here now because this stuff, if you don't understand equilibrium very well now, it'll make this unit pretty tough. But if you stick with it, it's not that bad. Um, and we talked a teeny bit of it about this at the end of last unit, but equilibrium is when the rate of reaction um, going forward is equal to the rate of reaction going backwards. And you can kind of represent it with one of these graphs where it's like you have the reaction taking place, and then once you hit equilibrium, you kind of hit constant concentrations. I mean, like there is going to be some flux back and forth, like you are still reacting, but you're not going to be favoring one side unless you do something to mess with it. Okay, so let's look at this graph here. Blue is reactants, red is products, and we're hitting equilibrium like right around here. Do we think that K is going to be less than, equal to, or greater than 1? Yep, exactly. So K, again, we learned is it's capital K now, not the lowercase k like from last unit, is equal to products over reactants. And if you have a lot more products at equilibrium, this is going to be a bigger number, meaning that it's going to be greater than 1. All right. Now I got a few true or false questions because again, a lot of this stuff as of now is conceptual. We haven't gotten into a lot of the math part yet, but um, true or false? Once equilibrium has been established, concentrations of the reactants and products become equal. False. Yeah. This is one of those ones that, it sounds like it would be true, but you can look up here and we see that we do have more products than reactants. So even though they're hitting constant concentrations, those are not equal to one another. So that's a very important thing to not mess up about equilibrium. And I think that's probably the easiest mistake to make is people think when you're at equilibrium, you have equal amounts of both things, but that's not true. Okay, next one, true or false? In a dynamic equilibrium, and the word dynamic means that we're at equilibrium, but we still have movement, we still have reactions taking place. In dynamic equilibrium, the forward and reverse reaction rates are equal. Yes, yep, that is true. That's the pretty standard definition of equilibrium, talking about the rates of reaction. All right, next one. The equilibrium constant, again, that capital K, changes when the concentrations of reactants or products is altered. This one's false. What is in the name? What's this word here? Constant. The only way we can alter a constant is by altering the temperature. Everything else, K is going to stay equal. And you're going to learn about this in a few classes, but there's something that has a weird name from some old scientist, I guess, called Le Chatelier's principle. Maybe talked about it in another class. Doesn't matter if you've seen that though. Um, yeah, temperature is the only thing that can alter K. Anything else might shift the position of equilibrium, but then what's going to happen is the reaction itself is going to go back to equilibrium. So it's going to kind of counteract that imbalance. So the constant itself, the K constant, is not going to be affected. So that's another really easy thing to mess up about equilibrium. And then I already told you this one. The only factor that can alter K is temperature. That's true. And there's an explanation for that that I don't even like totally understand. It's not something that Dr. Blumley expects you to understand either, but it has to do with like the speeds of the particles and stuff like that. All right, last one I think, yeah, of the true or false is that adding a catalyst to a reaction at equilibrium will change the value of KEQ depending on if the catalyst acts more in the forward or reverse direction. This one's also false. And so the wording here, I kind of made it purposefully tricky. Um, Basically, a catalyst is going to act on always the forward and reverse reaction equally. So it's not going to favor one or the other. And that's because and this does go back to something that we talked about in the last unit. We remember that when we kind of like look at one of these energy diagrams, we have this activation energy, right? And then maybe it ends up here or whatever. A catalyst is going to come through and it's only going to alter this part up here. So it's going to maybe it'll look more like this, right? It's lowering the activation energy. Well, if we think about it, if going this way is forward and going this way is reverse, by lowering this, we've kind of sped up both of those, right? Because if we lower this hump, now it's going to be quicker going this way and it'll be quicker going this way to an equal degree. And again, it's always important to remember that it is an equilibrium constant. So it's going to be constant for everything except for if temperature is altered. Okay. Anyone have any conceptual questions about equilibrium? It'll start to make more and more sense within the next couple days. Specifically, the thing you guys are learning tomorrow, ice tables, is I want to say something that you need to be doing for the next 2 months. So tomorrow's class is like a really, really important one going forward. Okay. An equilibrium system is set up as shown with Kc. And if you ever see the C in there, all that means is it's talking about concentration. You can also have Kp, where it's representing K in terms of pressure. And in fact, there is a formula to go from Kc to Kp. I don't know if you guys have seen that yet, but he'll show you that one soon. Kc is 3.0 times 10 to the minus 6. So right off the bat, is this product or reactant favored? Reactant favored, yeah. It's a tiny number times 10 to the minus 6. And here's the reaction. We have H2 plus I2 going to form 2HI. And I'm asking you to set up an expression for the equilibrium constant K. So all that I want you to do is represent it in terms of those products and reactants. And this is another skill that is 100% necessary to do the ice tables that you're going to do tomorrow. So all that we're doing here is we have to use those coefficients and then make sure that we're using the right phases of matter. So gases and I'm blanking on aqueous things are going to go in the equilibrium expression. Solids and liquids do not. And that basically comes down to the fact that solids and liquids, their concentration is so great that they don't even really play a role in the overall thing. So again, though, it's products over reactants. So that's going to look like this. We have the concentration of that product, HI, raised to the power of 2, because there's a 2 in front, over H2 times I2. And it's always multiplying, not adding or anything like that. So this is K, equilibrium. And now another skill that's important is sometimes you're going to be given the numerical values for concentration. So that'll be in terms of molarity, 9 times out of 10. And so here they are. And now plug this in, and I want you to try to find the value of HI. So we have Kc that was given to us in the problem, and we have the values of H2 and I2. Here's the answer that I got for this one. So again, we have everything we need except for that HI concentration. So I'm going to multiply the denominator on both sides, and then the way that I would go about canceling out that exponent of 2 is I find it really easy to simply raise whatever's in my calculator to the power of 1/2. That's the same as taking the square root.
Because the divide at the bottom
Mhm.
and then minus that by Casey.
Yeah, exactly. So I can put in KC first like this. Oh, not like that. 3 times 10 raised to the power of -6. So I always like to do that first, make sure the notation was good. And then I always spam parentheses whenever I can. So I would do multiplied by, and then in parentheses, 0.115 times 0.305, close the parentheses. And now all we have left is this equaling HI squared. So I would take this and I would raise it to the power, and again, always using parentheses, of 1/2. Cool. The last step there.
Wait.
Is it? Mhm.
And then you just times that by that. And then you
And then from there, that would be the square root or raise it to the power of 1.
can finish that one.
Yeah.
And then,
Two.
oh, thank you.
Mhm.
And you raised it to 1/2 because of the 2x product that we had.
Yeah, exactly. That's how we can cancel out the yeah, that exponent. Okay. So nothing too bad there, right? Very kind of elementary stuff. This is good setup though, because being able to plug into that K expression again is super important coming up. Next thing we did learn a couple ways of how when you have K, or wait, that's gonna be 9 and 10. Let's do this first. You guys did learn the formula for going from KC to KP, is that right? Maybe you did. Okay, well let me think that's it. Yeah, let's see if I can pull it up on your formula sheet. Do you know where he keeps that formula sheet?
I blacked it.
Oh, yeah, click on that,
On his.
click on that live, the highlighted one,
The highlight.
I'm like
not an actual link, click on,
No, up.
up.
right?
The
Stuff
thing-
is-
I see.
Live
Here,
pictures.
here we go. Got it. And okay, let me Google it. This is easier. Let's go KC to KP formula. There we go. This is it. KP, and this is given to you, I'm almost positive. RT to the power of delta N. Let's go back here. So I've given you KP as 100, sorry, and we're at 30 degrees Celsius. So we have T, we have KP, R is our gas constant. That's going to be the 0.0821, because we're going back from, I know we've used 2 different R's now. We're going back to that first one.
And then you find out by when the moles of the products react.
Exactly. Yeah, that's probably the hardest part of this is remembering what that means. And so we have 5 moles of gas on the product side and 3 on the reactant side. So it would be delta N is equal to 2. No, because it's all products minus reactants. Yeah, that's a good question. And also be careful, 30 degrees Celsius needs to be in Kelvin. So the way I would solve this is I would do everything in parentheses first, then put it to the exponent, and then divide by that.
That's fine. 0.8206.
Yeah, 0.08221, 206, whatever you want to do.
Oh, wait, we're trying to find.
Mhm.
And did the inside parentheses and you squared it?
Yeah, exactly. And then now I'm dividing it on both sides. Yeah, all this is, it's another one of those formulas where if you have the formula, it shouldn't be too tricky as long as you don't make any calculator mistakes. And the answer I got here was 0.161. Do we feel good about that? All right, so this next part is what I was about to start talking about. So this is where we have a K value and we have a equilibrium expression, and then we're doing something to it in the next part. We're either, flipping the reactants and products or multiplying or dividing the coefficients, doing something. And we want to find out what the new K equilibrium constant would be after we've done that. So let's go through. There's 3 different rules that you kind of need to know for these ones. So we'll talk about all 3. We have this first expression written as it's 2H2 plus O2 is at equilibrium with 2H2O. And K is given as 31 flat. The next part, though, we've gone, and now we have 2/3 H2O at equilibrium with 2/3 H2 plus 1/3 O2. So we've done a couple things here. Name one thing that we've done to this expression. Yep, we've divided everything by 3, or multiplied it by 1/3, either way. So yeah, all the coefficients have been divided by 3. And what else did we do? Yeah, exactly. So let's start with the fact that we flipped the expression. What do we do to K when we flip the reactants and products? Reciprocal. Not the sign. Yeah, we take the reciprocal of it. So right off the bat, we'll call this, yeah, we'll say 31 over here. So if this is K1 and this is K2, we're going to go 1 over K1 because we were taking the reciprocal. And then we also need to factor in the fact that we divided everything by 3. And so what do we remember what we do there when we divide something? So anytime you're multiplying or dividing the coefficients, you need to take that power as an exponent, or take that factor as an exponent. So in this case, we divided by 3. So we're going to raise the whole thing to the power of 1/3, which is the same as taking the cube root. Now, say we had multiplied everything by 3, we would put this to the power of 3. So that's the rules for dividing and multiplying. And we know that 1 to the power of anything doesn't matter. It's going to be 1. So really all we're doing here is going 1 over K1 to the power of 1/3. And we know what that is. So it's going to be 1 over 31 to the power of 1/3. And now I would first get that denominator looking better. So I would go 31 to the power of 1/3. See what that gets us is 3.14. So now it's 1 over 3.14. And so we can say that K2 is equal to 0.318. And that should make some sense, right? Because even though we divided by the coefficients, we know that the first one was very product favored, right? 31 is a lot greater than 1. So if something is product favored and we flip the products and reactants, it's going to make sense that now we have a value less than 1. that means it's reactant favored all of a sudden. Do we feel good about that? Okay, cool. Not as great. What part? So the first step here is we want to see what is different about this expression from the new one. So when we see this one, we can start off with the very first reactant. H2 is on the reactant side here, and it's not on the reactant side here. So that means it's now a product. And we see O2 is a reactant here. O2 is also a product here. H2O was a product here, and now it's a reactant. So that makes me go, okay, so we flipped the reaction completely. Reactants are now products, products are now reactants. And then we also want to look at what are the numbers in front of each thing. So if, right here we have a 2, and now it's 2/3. That looks a little bit weird, but let's go to the next one. This one is a 1, now it's 1/3. This one's 2, and now it's 2/3. So to me, that looks like everything got divided by 3. So we flipped the reaction and we divided everything by 3. So we're going to go over here and take the K value for that initial expression. The first thing we're going to do is take the reciprocal of it because we flipped the reaction. That's the step that you always do there. And that only means we put 1 over it. And then we have to raise it to the power of whatever factor we multiplied or divided by here. So if we divided by 3, we have to raise it to the power of 1/3. And that's all I did. Cool. Next one, and I think this is the last one I have, so it'll be kind of short today. We also learned that sometimes you can have equilibrium expressions where you have multiple different reactions and then you combine them into one. And all you do there is you take the two K values and you multiply them by one another. So let's see, we have Ag2SO4 in the first one. That's in the reactant side. If I look down here at the overall new reaction, that's still a reactant. So that looks good. And also it has a coefficient of 1 here and it has a coefficient of 1 here. So I don't see anything that we need to do to this first one yet. Now, if we go look at the second reaction, we see we have this big thing, AgNH3 This is a reactant over here. Now I see it as a product over here. And also it has a coefficient of 1 here, and now I see it has a coefficient of 2. What else do we see? We see Ag plus here, 2Ag plus here in the products, and we don't see it anywhere here, which makes me think, okay, then we know we flipped this one, and we know everything got multiplied by 2, so that's going to cancel these out. Does that part make sense? Maybe it'll help if I write it out myself. So, right, we have the first reaction. Where we kind of said we don't need to do anything to it. And I can tell because this is a product, this is a reactant in the first thing, and it's a reactant in the final one, and nothing's been done to its coefficient. The next one, though, looks a little bit weirder. So again, we said that this thing here is now a product. So that means we're gonna have to flip it. So let's do that real quick. Because this big thing here, this reactant, is a reactant in this second equilibrium expression, and then in the new combined one, we see it as a product. So that kind of is like making me think, okay, this is the only place in the entire thing where I see this weird looking reactant, and now it's a product. That means I need to flip it to the other side. Yeah.
So you have to try to see if I get the actions that we learned.
Yeah.
So if you need to multiply by 2
Mhm.
and then flip it, and then take the reciprocal K,
Mhm.
and you raise it to the power of 2.
Yeah, exactly.
Okay.
And so, yeah, you got the other part too. So we also recognize that in the overall combined reaction, this big thing has a coefficient of 2. So everything here has to get multiplied by 2. So this becomes 4, this becomes 2, and this becomes 2. And now we can go through and do some canceling. So we see that 2Ag plus is a reactant now over here, and 2 AG plus is a product in that first one. So that will completely cancel out. And then we see sorry, ignore this one. You don't need this guy because we already worked with it. We see all the other components looking good now, right? So we see Ag2SO4 coefficient of 1 in the reactants. We see 4 NH3 in the reactants. So that looks good to me. And then in the products, we see that we do have this guy 2 Ag NH3 2 and SO4 2 minus. Yeah, they canceled out once we flipped it and multiplied by 2. Yeah, so that's why it cancels out. Because since it's 2 Ag plus in the products of the first one, and then 2 Ag plus in the reactants of the second one, those cancel out. Yeah, it becomes an intermediate. So now we can go through and let's make it look clean. Let's make sure we're good. Yeah, in the second reaction. Yeah. And so after I've done that, this looks good to go. It's a big number. Let's see. Okay, so yeah, this is good. That makes me think, okay, we did everything right. K1, we haven't even talked about Ks yet. Let's get to that part. K1 is, you don't add, you multiply them. Yeah, so K1 was this.
Like the exponents, do everything out by an order of 1, basically. So
Yeah,
adding first multiplication of exponents.
yeah, that's a good way of thinking about it. I've never thought about that. If you got a math brain, that's better.
Dude, I fucked 8.
It's getting you somewhere. I've barely picked up some of these patterns, and this is like the limit of my math quality as a student is once you get past Chem 132, I can't do it. But we see this, and let's go through and think about what we did to K2. That's a 2, right? We flipped it first off, so we're going to do 1 over K2 because we got to take the reciprocal, and we multiplied it by 2. So we're going to put this whole thing to the power of 2. Now let's see what that new thing looks like. So K1's going to stay completely the same. 1 over, let's see what K2 squared is first. That's probably going to be the simplest way to do it. So this number squared is 1.44 times 10 to the minus 14. I think it's easier to do that first and then do 1 divided by that. And that's going to become a really big positive number. Because if we have a teeny number on the denominator, it all of a sudden becomes big. So now we have new K1. K1 is still the same, sorry. 2.5 times 10 to the minus 6. The new K2 is 6.94 times 10 to the 13, though. That's what you got? Okay, let's do, so the next step here and the final step is multiplying them together, right? Because we've taken 2. Yes, you got? Okay, let's do it. So I did this, and now I'm multiplying it by, I don't think that's going to be the answer I get. Because when you have a minus and a, yes, I end up getting the new K, so we'll say K3, I guess, is 1.74 times 10 to the 8.
The -19.
You might be, do you have this as minus 13 in your calculator?
No, I have.
Okay. There could be some small calculator mistake, but a good rule is that when you have scientific notation and you're multiplying, if one value, you can always simplify it down by if you have 10 to the minus 6 and 10 to the 13, your answer is going to be 13 minus 6. So it'll be 10 to the 8.
Yeah, okay, now I got it.
Okay, good. Yeah. Does that make sense? my work is kind of messy here, but it's very similar concept to what we did on the previous one. The only difference now is we're multiplying two K values together. And you also want to do all the manipulating to the individual Ks before you multiply them together. So multiplying the two Ks is the final step.
Why do that?
Because so we have one reaction here, another here, and in this final new reaction, we have both components of both of those combined. And so whenever you're basically combining two equilibrium expressions, that's how you do it. Yeah. So as a quick recap, there's three rules that you need to know. When you flip a reaction, you're taking the reciprocal, so you're going to do 1 over the K. When you multiply or divide, you're going to put it to the power of that factor. So it'll either be, if you're dividing, you put it to the power of like 1 over 3 or 1 over 2. If you're multiplying, you put it to the power of 2 or to the power of 3. And then the last thing is when you have two different K expressions and you combine them together, it's going to be K1 times K2.
So. And the first and the second, they didn't reverse at all, you would just, but like, they were multiplied by 2, you would just take it for the second power. Without having to do the reciprocal.
Yes.
Okay.
Yep. Cool. Anyone have any questions about this stuff? Sounds good.